Today we're going to be doing some lesson 5 practice. So this was the pH lesson, and we're going to be doing some calculations essentially very similar to the lesson 4 practice, except we're going to add in that one last step where we're going to turn these into pH values. So what is the pH of a 5.0 times 10 to the negative 5 molar magnesium hydroxide solution? So to figure this out, there are a couple of routes you can go. pH can be converted to POH by taking 14 minus pH, which will equal POH. Same thing, you could go the other way. You could take 14 POH, and that would give us pH. Also, we could convert directly from OH concentration. So if you have the concentration of OH, you can convert directly into POH by taking the log of OH. Or if you want to go from pH to OH, then you would take the 10 to the negative POH. And if you'd like to do that, you can copy and paste essentially the same thing. pH becomes the concentration of hydronium by taking 10 to the negative pH. Oops, what am I writing? 10 to the negative pH, and you can go from hydronium to pH by taking the negative log of H3O. And you can convert between these two by taking either the Kw divided by the concentration of H3O, or you can take the concentration of the Kw and divide it by the concentration of OH to get this value. So all you need to do in these kind of questions is decide which direction are you going to travel around this little circle. Are you going to go straight to a value for pH, or are you going to go to a concentration first and then go? So we're going to have this magnesium hydroxide. That's probably going to give us a hydroxide concentration. So we're thinking about how we're going to start here, but we want to end up here. So do we want to go this way, or do we want to go this way around the circle? And those are our two choices. Unfortunately, you can't just go in a diagonal. So first things first is I need to think about what is the dissociation of magnesium. So magnesium hydroxide, whatever the concentration of this, if you undergo the dissociation, there's going to be one magnesium, and so the ratio will be 1 to 1 with magnesium, but there will be 2 times the concentration of hydroxide, because we have a ratio of 2. So if our original concentration is 5.0 times 10 to the negative 5 molar, then the concentration, I don't care about this one, is going to be 10.0 times 10 to the negative 5 molar. Or if you're using your calculator, you're probably going to get a result of 1.0 times 10 to the negative 4 molar, because that's how the calculator should write it. All right, so now I have my OH concentration. So let's try, I like working in pH, honestly. I don't really like dividing by, I don't really like the Kw equation. I think it's a little clunky to work with because it's so easy to input it incorrectly in your calculator. So let's just go straight to a POH. So the POH will be equal to the negative log of 1.0 times 10 to the negative 4 molar. And that's a great number to work with because I don't even have to pull out my calculator. I just know that this is all base 10, so I can just bring that 4 down and I have a POH of 4. And now with that POH of 4, I'm up in the top corner here. So I'm going to go with a 14. I'm going to say that the pH is equal to 14 minus my POH. And so that means that my final result is 14 minus 4. and my pOH is 10, or my pH is 10. And that makes sense because that would be a basic pH, and I just dissolved the base in water. Okay, so here's some more practice for that. Let's just see if there's a more challenging question here. Okay, and these are all very similar. So let's try. We'll try one more of these, and then we'll go to this question 8, where we have some more of these challenging questions. So determine the concentration of hydroxide ions in solutions with the following pH values. So if the pH is 4.1, then we can figure out the pOH, which is 14 minus the pH. So I'm going to get a pOH equal to 14 minus 4.10. And so that's going to give me a 9.9, right? A 9.9 pOH, which means that my concentration of hydroxide is simply equal to 10 to the negative 9.9. Now this is not an accepted value. We don't like to see this, we don't like to see decimal values in the exponents most of the time. So it's very hard to visualize what that means. So I do expect that you're going to go to your calculators and you're going to type in 10 to the power of negative 9.9, and you're going to get a value that you can write out in scientific notation where the exponent will be a whole number. And we just got to double check, how much do we start with? We started with 3 significant figures, so we can go to 1.26 times 10 to the negative 10, and that's our molarity. And there we go. And we can do the same thing with this pH value of 5.1. I'm going to try a different route, so let's convert this pH directly to, let's go the other route down the other side of our list. We're going to go to H3O plus is equal to 10 to the negative pH. So that means that it's going to be equal to 10 to the power of negative 5.10. And let's try that out. So 10 to the power of negative 5.1. And so we get a value of 7.94 times 10 to the negative 6. And then I'm going to use my next equation. And this is, of course, H3O plus, hydronium. I'm going to use my Kw equation. Kw divided by the concentration of hydronium is equal to the concentration of hydroxide. So I can take 1.0 times 10 to the negative 14 and divide that by the 7.94 times 10 to the negative 6. And the value I get is 1e negative 14 divided by 7.94 e negative 6. Depending on the significant figures that you kept, you may or may not get the same answer. These questions in particular, when you're dealing with very small numbers, are very sensitive to your significant figures. 126 times 10 to the negative 9. And that's our answer. Interesting that the values almost come out to the same. We get a similar decimal values, but we do have a difference of 10. So that's the factor of the 0.1 and the 4 and the 5. So I believe you can actually probably deduce this if you know your exponent laws very well. Okay, so calculating the pH of the following solutions. Let's just go through and try one more of these. Let's do this barium hydroxide one. So barium hydroxide, again, we have to consider, the first thing we need to consider is that barium hydroxide does not dissociate into a single hydroxide, but it does dissociate into two. So we get barium 2 plus 2 hydroxides. And so this means that the concentration of 4.0 times 10 to the negative 4 is going to be equal to 8.0 times 10 to the negative 4 for the hydroxide. Now you have a hydroxide concentration. You can proceed in any route you'd like. I'm going to just do the POH route because I like playing with that. Equals POH. So I'm going to do negative log times 8.0 times 10 to the negative 4 equals POH. Let's try that out. Negative log, oops, don't use a log x, log 8e negative 4. And we get a value of 3.0969. And that is equal to POH. And now I can find my pH because that's going to be equal to 14 minus my POH. And so that's going to be simply 14 minus 3.0969, which is 14 minus 3.0969, 10.9, and my original value was 2 significant figures, so I actually can only really keep the 10. I can really just reduce this to 11. So pH 11. Okay, I think I'm going to end there, and I'll be back to talk to you about probably lesson 7, because I think lesson 6 is pretty straightforward. So lesson 7, where we're actually going to do some equilibrium calculations. Thanks for your time, and have a great day.